All right, welcome. If you're an O&M tech, you already know a solar plant is way more than just panels and inverters, right? Well, today we're diving deep into something absolutely critical, the high-speed world of protection systems. These are the unseen guardians that keep everything safe, reliable, and plugged into the grid.
So let's start with this quote. This single sentence, it's everything. It's the whole philosophy behind electrical protection. See, it's not just about, stopping a problem. It's about surgically removing it in milliseconds. So the rest of your multi-million-dollar asset can just keep humming along, making power. Speed, precision, keeping things online, that's the whole game right there.
Okay, so here's how we're going to tackle this. First, we'll get into the why this stuff is so important. Then we'll look at all the pieces and how they fit together, kind of like the whole ecosystem. After that, we're going to zoom right into the relay itself. Then we'll talk about setting it all up for success. And finally, the part you've been waiting for, how to actually troubleshoot trips and faults when you're out in the field.
All right, first up, the unseen guardian. Let's really dig into the fundamentals. Why does protection matter so much? Why do we put so much effort and hardware into this?
And look, it boils down to three core things, and this goes way beyond just, preventing a fire. Number one, and this is the most important, personnel safety. We're talking about your safety. Number two is protecting the gear. This equipment is expensive, and you can't afford to have it get fried. And number three, grid compliance. The utility has some really strict rules. If your plant starts acting up, they can and will kick you off the grid. So these systems basically make sure you're playing nice with everyone else.
Okay, moving on. A protection system isn't just one single box sitting on a wall. No way. It's a whole ecosystem of different parts, all working together in perfect sync. And honestly, the best way to think about it, it's like the plant's nervous system.
This analogy is just perfect. It makes everything click. So you've got your sensors, your CTs and VTs, right? Those are the nerve endings. They're out there 24/7, feeling and measuring the flow of power. All that information goes to the relay, which is the brain. It's constantly thinking, processing those signals, and deciding, is everything okay, or is something wrong? And if something is wrong, the brain tells the muscle, the circuit breaker, to act. And that muscle flexes, opening the circuit and stopping the fault dead in its tracks. So let's walk through that chain reaction, step by step. Boom, a fault happens. Let's say a big short circuit. Instantly, the CTs sense this insane spike in current, and they scream that information to the relay. The relay takes one look, compares it to the settings you programmed in, and goes, whoa, that's a fault. It immediately fires a trip signal to the circuit breaker, and bam, the breaker opens, isolating the problem. And the craziest part? This entire thing happens faster than you can blink. Literally. Okay, now let's zoom in on that core component. It's time to go inside the brain of the whole operation, the protective relay, and really decode what it's doing.
All right, this table right here, think of this as your pocket cheat sheet for the field. You're going to see these ANSI numbers everywhere, on drawings, on the relay faceplates, and in solar, these 5 are the ones you'll run into over and over again. You've got undervoltage, overcurrent, overvoltage, earth fault, and frequency. And there's a good reason these are so common, right? Solar plants are inverter-based, which means they talk to the grid in a unique way. So keeping a super close eye on voltage and frequency is just absolutely critical for keeping things stable.
So let's talk about the overcurrent relay, the 5051. This thing is a total workhorse. Its main job is to stop your cables and equipment from literally melting. But the key here is that it's smart. It knows the difference between a really dangerous short circuit, where it needs to trip instantly, that's the 50 function, and a harmless temporary overload, like when a big motor kicks on. For that, it has a built-in timer, the 51 function, that lets that little surge go by without causing a nuisance trip. It's pretty clever.
Now, the distance relay, or 21, is a bit more sophisticated. You'll usually find this on the big transmission lines that connect your plant to the main grid. So instead of just looking at current, this one measures something called impedance. Just think of impedance as electrical resistance, basically. The longer a wire is, the more resistance it has. So by measuring the impedance, the relay can actually calculate how far down the line the fault is. It's an incredible tool for pinpointing problems. Okay, so we've got all these different protective functions, right? But the real trick is, how do you get them all to work together like a well-oiled team? Well, that all comes down to setting them up right. And the key concept here is called coordination. This is really the art of protection engineering. Think about it. If you get a small fault in one single combiner box, the last thing you want is for the main breaker for the entire plant to trip, right? That would be a disaster.
No, you want the fuse or the breaker that's closest to the problem to open first. Good coordination means you isolate the smallest possible part of the system, and that does two things. It keeps the rest of the plant making money, and it makes finding the fault way, way easier for you. And within this whole coordination scheme, you've really got two layers of defense. First, you have your primary protection. Think of this as your frontline soldier. It's fast, it's designed to clear a fault in its zone, and do it right now. But what if it fails? What if the breaker itself jams or something? Well, that's when your backup protection kicks in. It's a bit slower and it's usually upstream, but it's there to trip and prevent a total catastrophic failure. It's your ultimate safety net.
Okay, this is where the rubber meets the road. An alarm is blaring, a breaker's tripped, and everyone's looking at you to figure out what on earth just happened. So, let's walk through how you should approach this. Let's take a classic case. You're getting frequent overvoltage trips. Now, the single most important thing here is to be methodical. Whatever you do, don't just walk up and reset the relay, please. You have to start with the data. Pull up the protection settings, look at the voltage logs from your SCADA system. Is the grid voltage actually high, or is something else going on? Only after you've looked at the data should you start physically inspecting things like wiring and connections.
The relay itself is trying to tell you a story. It's packed with information. So learning how to read its event log or even just the front panel is a huge skill. This little table here is a great starting point. For example, if you see the relay pointing to R phase and Y phase, you're probably hunting for a phase-to-phase fault. But if it just shows R and Earth, well, now you know you're looking for a phase-to-ground fault. It's like being a detective. It helps you narrow down the suspects right away.
Okay, but what about those times when a relay trips and there's nothing actually wrong with the power system? Ugh, the dreaded nuisance trip. So if you think that's what's happening, where do you even start looking? Well, let's go right back to our nervous system analogy. The problem probably isn't with the muscles. It's in the nerves, the CT or VT wiring, or maybe the sensors themselves are faulty. Or it could be the brain's programming. The parameters in the relay are just wrong.
And that really brings us to the final and most critical question you have to ask yourself every single time a trip happens. Is this a true fault, or is this just a nuisance trip? Your ability to dig into that relay data, compare it with the SCADA history, and make that call quickly and correctly, well, that's what separates a good tech from a great one. Getting it right saves a ton of time, it slashes downtime, and at the end of the day, it's what keeps your plant running safely and making money.